Hello everyone, welcome back. Myself Janavi J from Sri Venkateshwara College of Engineering, holding the USN 1BE21IS022. Today, we're going to look into a key distribution scenario, which is the topic of cryptography and network security. So, without any further ado, let's get started. So what is a key distribution scenario? Before going to what the key distribution scenario is, we have to know what a key distribution center is actually. The use of key distribution center is based on two level of hierarchy. At a minimum, two level of keys are used. Two keys are used. One is the session key and the other is the master key. Master key is used to encrypt the session key. So, communication between the end user is encrypted using a temporary key, often referred to as a session key. So, session key is a temporary key which is used to secure the communication between two end users. Let's say user A and user B. Typically, the session key is used for duration of a logical connection and then discarded. So basically, the session key is only used for one logical connection, and after the lifetime, it is discarded, and a new session key is generated for the next scenario. Master key is shared by the key distribution center and an end system or the user and used to encrypt the session key. So this is the key distribution scenario. I'll first go through the slides, then I'll explain you with the diagram. Okay. So you have an initiator A, responder B, and the key distribution center is at the top. So let's go to the scenario of events that takes place. First, let us assume the user A wishes to establish a connection with the user B and requires a one-time session key to protect the data transmitted over the connection. A has a master key KA only known to itself and the KDC. Similarly, B shares the master key with KB with the KDC. So what the slide tells us, we have an initiator here. So A wants to establish a connection with B, but before establishing a connection, it has to share the details so that the key distribution center can provide with the session key. So before that, initially there is a KA which is known to the key distribution center and A, and that is KB which is known to the key distribution center as well as B. No other users know about KA and KB. Okay. Next, A issues a request to the KDC for a session key to protect a logical connection to B. So first, A is initiating a connection. The message includes the identity of A and B and a unique identifier nonce, which is called as N1 for the transition, which we refer to as a nonce. The nonce may be a timestamp, a counter, or a random number. The minimum requirement is that it differs for every request. So for each request, there is a new nonce, or it should be unique. As to prevent masquerade, it should be difficult to an opponent to guess the nonce. So a random number is a best choice for the nonce. So you can say this is the first step. You can see here that is it's labeled as 1. So firstly, user A or initiator A sends a request to KDC having the ID A, which is the identifier of A, ID B, identifier of B, and a nonce N1, which is random. Okay, this is the first step. Now second step, what happens? Let's see. Now, the KDC responds with a message encrypted with a KA. As I mentioned earlier, KA is only known to the KDC and the initiator A. Thus, A is the only one who can successfully read the message, and A knows that it is originated from the KDC. The message includes two items intended for A. So, one, the one-time session key, which was needed, KS, to be used for the session to send the message to the B. The original request message. So with the session key, there is also the original request, the IDA, IDB, and nonce one, which was sent by A to the KDC, that is also included in the nonce. To enable A to match the reason with the appropriate request, so that A knows that this is the request which it sent and it's original. Thus, A can verify that it's the original request. Then it is not been altered before reception by the KDC, and because of the nonce that this is not a replay of some previous message. In addition, the message includes two items intended for B. For B also there are two items. One is the one-time session key KS to be used for the session and the identifier A. Its network address IDA. These last two items are encrypted with KB, the master key that the KDC shares with B. They are used to send to B to establish a connection and prove A's identity. So in the second step, you can see the key distribution center sends two responses. Okay, in one response which has two fields. One is the let's see the KA part. It is encrypted with the KA, the private key of A. with the KS, the one-time session key, the original request, that is the IDA, IDB, and N1, as well as there is one message for KB, which has the session key, and IDA to tell A that A is the initiator of the request. Okay, this is sent to the initiator A. Now from there, next what happens? Let's see. A stores the session key for the use in the upcoming session and forwards it to B, the information that originated at the KDC for B, namely EKB, that is the encryption with the KB private key of B, the session key with the IDA, that is the identifier of A. Because this information is encrypted with KB, it is protected from eavesdropping. B now knows the session key KS, know that the other party is A from IDA, and know that the information originated at the KTC because it is encrypted using KB. At this point, a session key has been securely delivered to A and B, and they may begin communicating with each other. So, in the third step here, you can see that A sends a message to B, which has been encrypted by private key of B, which was originally sent by the key distribution center. So, and the session key and the identifier of A. Now, B knows what and all things B know. IDA, which is who is sending the request, the session key, and B is sure that it is sent by the authorized people because it has the private key. That is a key distribution center only has B's private key. Okay. So now both the initiators A and the responder B both have a session key shared. Now using the newly minted session key for encryption, B sends announce N2 to A. Now before this, in the third step, they can carry on the message. That's it. So from here, when the session key is exchanged, further communication can be proceeded. But fourth and fifth step are additional authorization steps. So what it happens is, usually the newly minted session key, that is the KS for encryption, B sends announce N2 to A. Also using the KS, A responds with announce N2 function, that is perform some act transformation on K2. Example, adding a 1 or something, some transformation. Okay. These steps assure B that the original message it is received and it was not a replay. Note that the actual key distribution involves only steps 1 to 3, but the steps 4 and 5 as well as 3 perform an authentication function. So see, in fourth step, a key using the newly minted key session key, that is KS, B sends a N2 nouns to the A, and A responds with some function on the N2 nouns as well as the session key B. So this is the scenario. You can see step 1, 2, and 3 are key distribution steps. 4, 5, and 3 as well is authentication steps. So after 1, 2, 3 only, people can start. That is the user A and user B can start securely communicating with each other. So this was about the key distribution scenario. Let's see what are the major issues with key distribution scenario. So when we think about key distribution scenario, we have two major issues. One is the hierarchical key control and the other one is the session key lifetime. So what is hierarchical key control? Hierarchical key control. It is not necessary to limit the key distribution function to a single KDC. Indeed, this is very bad choice if we have multiple network or a very large network with many users. As an alternative, a hierarchy of KDC can be established. For example, there can be a local KDC, each responsible for a small domain of networks or such as a single LAN or a building. If two entities in different domains desire to share a key, they can do the communication using the corresponding local KDC and communicate to the global KDC. The hierarchical concept can be extended to 3 or even more layers depending upon the population and the geographical scope of the network. A hierarchical schema minimizes the effort of the original, that is the master KDC, to distribute the master key because most master keys are those shared by the local KDC itself within its own entity, but that is within its domain. A local KDC can share its own master keys. Okay. Now, session key lifetime. The distribution of a session key delays the start of an encryption process and places a burden on a network capacity. A security manager must try to overcome these competing considerations in determining the lifetime of particular session key. For connection-oriented protocols, one obvious choice is to use the same session key for the length of the time the connection is open, using a new session key for the next one. If a logical connection has a very long time, then it will be prudent to change the session key periodically. For a connection-less protocol, such as the transaction-oriented protocol, there is no explicit connection initiation or termination. So what we do, it is not obvious that how often the key needs to be changed. So what we do is a better strategy is used to session key for a certain period of time or for a certain number of transactions. Okay, so this is all about the key distribution scenario. So that's it for today. Thank you. Please do like, share, and subscribe.